Hey, how's it going, everybody? All right, you're going to notice that we have taken quite a shift in our focus in our Math SL journey here. We've been working on algebra concepts for a while, and now what we're going to get into is trigonometry for the next two chapters. All right, I think you're going to enjoy it quite a lot. It is quite different than what we've been working with, and so your success there won't determine your success here or whatsoever at all. Anyway, let's get into trigonometry. What we're going to do in this chapter, the first chapter of trigonometry, is we're going to focus on right triangles and non-right triangles and the trigonometry associated with that. And then in the next trigonometry chapter, chapter 13, we'll start getting into what's called circular trigonometry, which is a pretty cool thing as well. All right, your goal for this first video in right triangle trigonometry is that you're going to learn to use the sine, cosine, and tangent ratios to find unknown measures in right triangles. And we're focusing on right triangles specifically. All right, there's some rules that you need to learn, some definitions that you need to learn, probably, to begin this video. And to lead you up to understanding those definitions, I want to take a look at similar triangles, of which I've drawn a pair on your screen. All right, you can tell that these triangles are similar because if you look at the ratios between the corresponding sides, they're the same. 4 to 6 is a 2 to 3 ratio, right? 6 to 9 is a 2 to 3 ratio, and so those triangles are similar to one another. Hypotenuses would have to have a 2 to 3 ratio as well. Now, if you do use Pythagorean theorem to try to find the length of the hypotenuses and you simplify the radical expressions that you get, the hypotenuse for the first triangle becomes 2 squared root of 13, and the hypotenuse for the second right triangle becomes 3 squared root of 13. And just to emphasize that whole similarity deal, 2 squared root of 13 over 3 squared root of 13 is still a 2 to 3 ratio. So I've got some similar triangles. Now, what I'd like to focus on here is the ratios between the sides within a single triangle. All right, so looking at this first triangle, let's say I wanted to make a ratio between the two legs of that triangle, AC and BC. All right, well, the ratio between what I'm calling leg 1, I'm going to say the left leg is leg 1 and the bottom one is leg 2. The ratio between leg 1 and leg 2 is 4 to 6, or a 2 to 3 ratio. Now, it's coincidental that that's the same as the scale factor that I showed you between the two triangles. Not coincidentally, if you check out the ratio between the left leg and the bottom leg in the other right triangle, you get 6 to 9. That's also a 2 to 3 ratio. All right. Well, in a right triangle, remember you got the two legs and you've got the hypotenuse. What if I try to make a ratio between the left leg and the hypotenuse of each of these triangles? In the smaller triangle, that ratio would be 4 over 2 squared root of 13, which if you do some canceling of that 4 and the 2 becomes 2 over the square root of 13. Well, again, not by coincidence, if I make a ratio between those corresponding sides in the other triangle, the left leg and the hypotenuse, that's 6 over 3 squared root of 13, and if you do the canceling with the 6 and the 3 like we did with the 4 and the 2, it's going to become 2 over the square root of 13. All right, and I'm going to continue this. We compared the two legs with one another. We made a ratio between the left leg and the hypotenuse. Let's make a ratio between the bottom leg and the hypotenuse of each triangle. In the smaller triangle, that would be 6 over 2 squared root of 13, which would simplify to 3 over the square root of 13. In the second triangle, that ratio would be 9 over 3 squared root of 13, which also simplifies to 3 over the square root of 13. All right, so here's the point that I'm trying to make. If you know that two triangles are similar, then the ratios between any pair of sides in one triangle are always going to equal the ratios between the same pair of sides in another similar triangle. Now here's another way I want you to look at this. You'll learn how to do this later in the video, but I have determined that the angles in these triangles, the acute angle measures, are 34 degrees and 56 degrees respectively. Okay, now what somebody's done is figured since every triangle that has 34, 56, and 90 degree angles is similar to every other 34, 56, 90 triangle, that we can memorize the ratios between any two sides, between the two legs, between a leg and a hypotenuse. And I've shown you that those are always the same. And those ratios have been given special names. They're called sine, cosine, and tangent ratios. I'm going to teach you a little bit more about those. All right, but all the sine and cosine and tangent ratios is what people have determined are always true for right triangles with certain measures. Like if you had a 20-degree angle and a 70-degree angle and a 90-degree angle, every triangle with those angle measurements, the ratio between its leg and the hypotenuse would always be the same, for instance. All right, well, let me define sine, cosine, and tangent. I've got a picture here of a triangle ABC, a right triangle ABC, and you see this Greek letter theta representing an angle measure there. We'll talk more about that in a moment. Actually, let me put another Greek letter in on the other side. Let's say that this other angle is going to be represented by beta. And I also want to teach you how you label the side lengths of a right triangle according to what's called standard labeling. You see, I've got angle A over here, and what we do is we name the side lengths of a triangle according to the name of the angle opposite that side. So the side that's opposite angle A is over here. What we're going to do is we're going to label that lowercase a to say it is opposite of that uppercase A angle. You see the angle B right here. We're going to label this side opposite that lowercase b, and we'll label the hypotenuse as lowercase c because the right angle was named C. All right, I said we're going to learn about the sine, cosine, and tangent ratios in right triangles. Now, when we're making a sine, cosine, or tangent ratio, those names are basically telling us which two sides of a right triangle we're making a ratio between. And there's only a couple of possibilities. We can either make a ratio between the pairs of legs, or between one leg and the hypotenuse, or the other leg and the hypotenuse. Now, we have to have a reference point in order to be properly able to determine which sides we're comparing, and that's what the angles are. You see that I wrote that we're going to find the sine of theta, the cosine of theta, and the tangent of theta, meaning that all the sides and angles that I'm going to mention are in relation to this angle theta as far as their position in the triangle. Now, the sine of an angle happens to be the ratio between its opposite leg and the hypotenuse. And since I'm finding the sine of angle theta in particular, the opposite leg is A. The hypotenuse is going to be C no matter where theta was located. So we're going to get A over C for the sine of that angle theta. Then the cosine of an angle is always a ratio between its adjacent leg and the hypotenuse. All right, now when we're finding the cosine of theta, there's theta. There are two sides of the triangle that are adjacent to or touching that angle, this side AB and this side AC. However, only one of those is a leg of the triangle, and that's the side AC, which I also labeled as B. So the cosine of theta is going to be B over C. Now, at this point, we've made a ratio between each leg of the triangle and the hypotenuse. The only ratio we haven't made yet is the ratio between the two legs of the triangle, and so that's what the tangent of theta is. And specifically, it's a ratio between the opposite leg and the adjacent leg from an angle. And from theta, we already said the opposite leg is A and the adjacent leg is B, so that would be A over B. Okay, so that's all sine and cosine and tangent tell you is which two sides of a right triangle you're making a ratio between. Now, just to kind of embed that a little bit further into your minds here, I just found the sine, cosine, and tangent of the angle theta. What if I'd used this angle beta instead? Well, the idea is still the same, just the actual sides of comparing would be different for the sine, cosine, and tangent. So the sine of beta, which, by the way, notice I abbreviated that as SIN. We're going to start doing that from now on. Is still a ratio between its opposite leg and the hypotenuse. It's just that from beta, B is the opposite leg. So we would get B over C. Then the cosine of beta is still a ratio between the adjacent leg and the hypotenuse, but from beta, the adjacent leg is A. Hypotenuse is still C, so we'll get A over C. And the tangent of beta is a ratio between the legs still, and there's only the same two legs here. It's just they again switch orders. Opposite leg over adjacent leg is b over a if you're looking at it from angle beta instead of angle theta. All right, so that's how you make trig ratios. Now let's see how you use those to do some very specific things. What I want to show you is how to find the missing side lengths in a right triangle using trig ratios, and then how you find the missing angle measures in a right triangle using trig ratios as well. You're going to need your calculator for this. You're going to need to make sure that it's set to degree mode. If you're not sure how to do that, read the instructions online or wait for class and I can show you. And you can see in this triangle that I know it's a right triangle first of all, which is key for what we're doing. And I told you one of the acute angle measures. We could easily find the other one if we just subtracted from 90. And we're trying to find two of the three side lengths. We do know one of the side lengths, the length of one of the legs. Okay, so how are we going to do that? Well, whenever you're trying to use trig ratios to find missing side lengths, you have to have an angle measure as a point of reference so that you know where the opposite and the adjacent legs are. And we're given one of the acute angle measures. Never use the right angle, always use an acute angle. We're given one of the acute angle measures, and we're given the side length that's opposite from that. Well, let's say we're trying to find the value of x, which represents the hypotenuse. If I want to make a ratio that compares the opposite leg of a triangle to its hypotenuse, that's going to be a sine ratio, as we just said in our previous slide. And so I can make this trigonometric equation. I can say that the sine of that 27-degree angle is equal to 15 over x. All right, opposite leg over hypotenuse. And then what I can do is use some basic algebraic manipulation to be able to solve for x. What I'm going to do is multiply both sides by x to get it out of the denominator. Let's make this x sine of 27 degrees equals 15. And then to get x by itself, I can just divide by that sine of 27 degrees. Now let's use three significant figures. Let's go the standard IB route. As long as your calculator's in degree mode, you're going to get this. Divide 15 by the sine of 27 degrees. And you're going to find that x is approximately 33.0. That 0.0 is important because we rounded to that. This thing was not exactly 33 units long. All right, so that's how we found the value of x. Now let's find the value of y. And what we're going to do there is we're going to use the 27-degree angle as a point of reference again. And we're going to try to make a ratio between the side that we know and the side that we're trying to find. Now, the 15, again, is the opposite leg from the 27-degree angle. And now the y is the adjacent leg. If you want to make a ratio between the opposite leg and the adjacent leg, you use a tangent ratio to do that. Which means this is the trigonometric equation that we'll write. We'll say that the tangent of the 27-degree angle equals 15 over y. All right, and then from there it's the same basic algebra that we just did. We'll multiply both sides by y, like so, and then we'll divide both sides by the tangent of 27 degrees to get y by itself. That'll get you 29.4. All right, hopefully you're finding that pretty simple. I want you to try one more example where you're finding missing side lengths. Now, I'm not going to narrate this entire thing, but I will write it in the work so that you can check yours here in a moment. And then we'll look at how you find missing angle measures. So let me add the variables that I forgot to add here, and then let you go ahead and try that problem. All right, now here's the equations that you should have had. When you're trying to find the value of x, use the 54-degree angle as a point of reference. X is the opposite leg, and the distance that you're given is the hypotenuse, and the ratio between the opposite leg and hypotenuse is sine. So the sine of 54 degrees equals x over 8. Similarly, when you're trying to find the value of y, that's the adjacent leg to that 54-degree angle that you're trying to find, and you still know the hypotenuse, so you make a ratio between the adjacent leg and hypotenuse. That's a cosine ratio, so cosine of 54 degrees equals y over 8. Then to solve each of these, you just got to multiply both sides by 8, and you got your answer. 6.47 and 4.70 respectively. Okay, now here's the next thing we're going to do. We're going to find missing angle measures, as I mentioned, and you can see in this case, when I'm talking about the missing angle measures, we have to know what's a right triangle, so we're going to know that that's 90 degrees, but it's the two acute angle measures that we don't know. And I gave you two side lengths. In order for this to work, you have to know at least two of the three side lengths of the right triangle. Now, some of you happen to know this Pythagorean triple that I'm working with. You see if the leg is 12 and the hypotenuse is 13, that you automatically know the other leg has to be 5. Not necessary to know that to answer this question, but thought I'd fill that in. We're going to make some trig equations in order to be able to figure out the values of alpha and beta. All right, now let's say we work with alpha. And let's say that we're going to compare alpha to the two side lengths that were originally given to us. Now from alpha, this 12 is the adjacent leg, and the 13 is the hypotenuse. So a trigonometric equation that I could write that relates those three measurements is this. I could say that the cosine of alpha, I don't know a number, so I'm going to put the name of the angle there. The cosine of alpha is equal to 12 over 13. All right, so now I've got to teach you something new algebraically. If you know what the cosine of an angle is, and you're trying to find that angle measure, then what you're going to do is use the cosine inverse function to be able to figure out what the angle measure is. All right, that would mean that alpha would equal this. Pay attention to the way this is written. Cosine inverse, it looks like cosine to the negative first power, but that's word cosine inverse, of 12 over 13. Now on your graphing calculators, if you can find where cosine is, right above it, it says cosine inverse. All right, and so then you type in the cosine inverse of 12 over 13, and it tells us that angle alpha is approximately 22.7 degrees to three significant figures. Now let's find the angle beta. There's actually two different ways we can find this. I'm going to use a more complicated way first just to make sure that you understand or reinforce this whole trigonometric idea. Then I'll show you the easy way. Beta, well, we're still going to use the side that's 12 units and 13 units long to find that. But now the side that's 12 units long has the opposite leg. The 13 is still the hypotenuse, right? And if you're comparing the opposite leg and the hypotenuse, you're using a sine ratio. So we can make this equation that the sine of beta is equal to 12 over 13. And then when you have the sine of an angle that you know, and you want to find the angle, use sine inverse in the similar way to how you used cosine inverse a moment ago. We can say that beta is equal to the sine inverse of 12 over 13. And you'll see sine inverse right above the sine function on your calculator. Use that, and you'll get that beta is approximately 67.4 degrees. Okay, now the thing I want you to notice here is that these two angles added together, 67.4 plus 22.7, add up to 90. It's a little bit off because of the rounding here. It gives you 90.1, but those are complementary angles because, well, they're the acute angles of a right triangle. They have to be complementary to one another. Now, let's talk about an easier way to find beta. Once you knew that alpha was 22.7 degrees, you could have done 90 minus that to figure out that beta was 67.4, but it works just as well to use the trig ratio also. One more example for you to try. Again, you're trying to find missing angle measures, the acute angle measures in a right triangle. If you're given two of the side lengths, I happen to give you the two legs rather than a leg and a hypotenuse like in the last one. Try it out, see what you can do. Starting with alpha again, you can see that the two side lengths that you know are the opposite leg and the adjacent leg, respectively. That means we're going to use the tangent ratio to compare them. We can say that the tangent of alpha equals 31 over 20. So then alpha equals the tangent inverse of 31 over 20. And thus alpha is about 57.2 degrees. All right, and then this time I'm going to use that little shortcut that I mentioned on the last problem in order to find out what beta is. Beta is simply going to equal 90 degrees minus alpha. And that's going to give us 32.8 degrees. All right, so you've learned what the basic trig ratios are, sine, cosine, and tangent, and how to use those to find missing side lengths and missing angle measures in a right triangle. Thanks for watching. See you next time.